Hello everyone, in this video I'm going to do a little bit of proofing. So this is part of introduction to real analysis, so you can use this video maybe as a helper for proving that a function is continuous at let's say a point C. So in this question says that proof that x squared is continuous at any arbitrary point C using from epsilon delta definition. So if in high school especially, to prove that x or any function is continuous at point C, we have three points. So f of C must be defined. Our limit as x approaches C of our f of x must exist, and our when we take the limit as x approaches to C of our function of x is equals to function of C. Okay, we learned this in high school. For college, we use epsilon delta definition to prove if the function is continuous. In this case, we need to prove x squared if it's continuous. So the formal definition of continuity at some point C is that if f, okay, I'll just say not right. So if f was continuous at the interval I, right? So if f was continuous at interval I, that means f must be continuous on any arbitrary point C in the interval I. Okay. So so for all C in the interval I, and for all epsilon greater than 0, this is for the formal definition of continuity, there exists a delta, there exists a delta which is greater than 0, such that the distance of x minus C will be greater than 0 and will be less than delta, and that implies that our distance of function of x and function of C will be less than epsilon. Okay, so using this we can prove if x squared is continuous at any arbitrary point C. So let's get started. So we want our x the distance of f of x and f of C will be strictly less than epsilon. S- um, while the distance x minus C will be strictly less than delta and greater than 0. So whenever this happens, so our function of x will be x squared is less than is minus by function of C would be C squared, and that will be less than our epsilon. Well, this is a perfect square, so we can factor it out. And using the property of absolute value functions, we have this can be split into x minus C. Let's write it as x minus C times by x plus C is less than epsilon. Okay, now we need to have a boundary, an upper boundary. So we want x plus C to not be like a very big number or goes to infinity. So we need to have a boundary, a restriction that delta is less than equals to 1. Okay, so in that case, our distance x minus C must be less than 1. Okay, using that, we have our, let's do it here. X minus c must be in between -1 and +1. That's the definition of the absolute value function. Okay, so now we need to put it in between, so in the middle, as x plus c. So we add by 2c on both sides. X plus c must be less than 1 plus 2c, and -1 plus 2c. Okay, so to make this clean boundary, we use a triangle inequality. So if we have x plus c, right, x plus c, well, it's the same thing as what? Now let me close to here. X plus c is the same thing as our absolute of x minus c plus by 2 c, right? Well, this will be less than or equals to absolute of x minus c and plus by 2 absolute of 2c, right? Well, this will be less than what? X minus c and add by 2 times absolute of c. While x minus c is less than 1, that means this will be strictly less than 1 plus 2 times absolute of c. Okay, so now so x plus c must be strictly less than 1 plus 2 times absolute of c. Using that, we have our, again, absolute of x minus c times x absolute of x plus c. This must be less than what? Our absolute of x minus c. Then if x plus c was strictly less than 1, that means it's less than 1 plus 2 uh, times absolute of c. So times 1 plus 2 times absolute of c. Well, this will be less than our epsilon. So we can have x minus c will be less than our epsilon over 1 plus, let's do this, 1 plus 2 times absolute of c. Okay, so we have our boundaries. So we have our delta must be in the minimum of what? 1 and epsilon over 1 plus 2 times absolute of c. Okay, so using the formal definition, we have c is in the real number. So given, or c was given, epsilon was given epsilon is greater than 0, we choose delta as our minimum value of 1, the interval 1, and epsilon over 1 plus 2 times absolute of c. Okay, if this was strictly between um, x minus c and it has then delta, then we know two facts, right? So the first point would be since delta was less than or equals to 1, right, our absolute of x minus c is less than 1. This one has to, we have so we have this one is less than 1. That implies that our absolute of x plus c must be less than our what 1 plus 2 times absolute of c. This is called implies. Okay. Now, the second point is, since our delta is less than or equals to um, epsilon over 1 plus 2 times absolute of c, then we have delta, no, we have x minus c must be less than what? Our epsilon over 1 plus 2 times absolute of c. Okay, now uh, once we have that, we need to substitute the boundaries. So x plus c, if we have, all right, x squared minus what, c squared is less than epsilon, that means x minus c and x plus c. So substituting the boundaries, x minus c is strictly less than epsilon over 1 plus 2 times c, so epsilon over 1 plus 2 times absolute of c, and our x plus c must be strictly less than what, 1 plus 2 times absolute of c, so times 1 plus 2 times absolute of c. Well, this cancels out, which leaves us with epsilon. Okay, so this proves that x squared is continuous at any arbitrary point c using the from epsilon delta definition. So we do a closed box as a symbol that we have proven. So that's it for this video. I hope you enjoyed this video and see you on the next.